One thing matrices are really good for is solving simultaneous equations. For example, if I have 4x plus 2y equals negative 2 and 4x minus y equals negative 11, that's a system of linear equations. Of course, I could use substitution or linear combination or elimination to solve that. Or I could use matrices. First thing I have to do is make a matrix of the coefficients, 4, 2, 4, negative 1. And notice I made a matrix of the variables. X I came to first, followed by y. So I wrote x over y, and finally a matrix of the answers. Now, let's take a simpler problem. 5x equals 10. What I would do is we divide both sides by 5 and get x equals 2. Or you could say, well, I'm really multiplying by the inverse of 5 on both sides, and I get x is equal to 2. 5 to the exponent of negative 1 is really like dividing by 5. Well, we're going to use that same principle here. To get x and y all alone and solve for x and y, I'm going to multiply by the inverse of 4, 2, 4, negative 1 on this side, and I'm going to multiply by the inverse of 4, 2, 4, negative 1 on that side. In other words, I'm going to multiply by a negative 1 here and multiply by a negative 1 there. Because a negative 1, or the inverse of a times a, will give me my identity, and the identity times xy is just xy. So that's how I'm going to get my xy's all alone. Well, more formally, if a system of equations is represented by the matrix equation, matrix A times x equals b, in other words, that will be our matrix of coefficients times matrix of variables equals matrix of answers if we're talking about linear systems. Where matrix A is non-singular, in other words, its determinant is not equal to 0, in other words, the inverse exists, then A times x equals b really means the inverse times a times x equals the inverse times b. We've just multiplied both sides by the inverse, and the inverse times a will be our identity, times x just gives us x, will equal to the inverse of a times b. Solve this system of linear equations using the matrix method. Of course we could use linear combination or substitution, but they ask us to use the matrix method. So we use the 4, 2, 4, negative 1 as our matrix of the coefficients, x, y, written x over y as the matrix of the variables, and 2, negative 11 as the matrix of the answers. And I also know that A inverse times A is equal to I. So what I'm going to do is I'm going to introduce a negative 1, or the inverse of my a here, and I'm going to multiply it on both sides. So what is the inverse of that? Well, the inverse is 1 over the determinant, which is 4 times negative 1 minus 4 times 2, times I switch this, and I take the negative of that and the negative of that, and when I multiply out, I get my inverse of a is equal to this. I'm going to multiply this on both sides. So here I'm going to multiply by 1 over 12, 1 over 6, 1 over 3, and negative 1 over 3. We've already covered how to find that inverse. Well, if I multiply by the inverse there, I must also multiply by the inverse there. 1 over 12, 1 over 6, 1 over 3, and negative 1 over 3. In reality, you're going to be using your calculator 99% of the time to find this inverse of A and inverse of A. But the key is the method. You're going to have to multiply that by this there, which was going to give us xy. That's what we're going to want to have isolated at the end. And when you multiply this 2 by 2 matrix with this 2 by 1, a 2 by 2 times a 2 by 1 will give us a 2 by 1. It will give us what our xy is. It will give us a 2 row by 1 column. And when you do that all out, eventually you get negative 2 and 3 when I multiply this matrix times that matrix. Which means that x is negative 2 and y is 3. Negative 2, 3 is the point of intersection of these two lines. We did have a solution here because the lines intersect, but our lines could be parallel with no intersection point. We'll get no solution here, or they could be on top of each other, so we get infinite solutions. If we tried to solve these simultaneous equations using the matrix method, we'd be very frustrated. 4x plus 4y equals 12, 4x plus 4y equals 16. Matrix of the coefficients, matrix of the variable, matrix of the answer. When you try to find a negative 1, or the inverse, 4 times 4 minus 4 times 4, 1 over that, that's the determinant 1 over that to get your inverse, you're going to get an error message because this is a singular matrix. These lines are, in fact, parallel, so you have to go to your old methods of substitution or elimination. Similarly, these are the same lines. If we take this and multiply both sides by 4, we get this line. These lines are going to be one on top of each other. Matrix of the coefficients times matrix of the variables equals matrix of the answers there. 4 times 1 minus 1 times 4, you're also going to get a singular matrix because your determinant is 0. 1 over 0 times your other one, which is mixed up in the negatives. You're not going to be able to get this inverse. You get an error message again because the lines are coinciding. Go to your old methods, which is elimination or substitution. The matrix method won't work here. This is what matrices are really useful for. If we have 3 equations and 3 variables, of course we can go solve 3 equations and 3 variables by substitution or elimination. That takes a whole page and it's very long and complicated. Or we could recognize we have a matrix of the coefficients, a matrix of the variables, and a matrix of the answers. In other words, we can set this up as a times x equals b. Well, if you're going to solve for x and you want to multiply both sides by the inverse of a, which will leave us x alone is equal to the inverse of a times b. Well, that's what we do to both sides. We get x, y, z is equal to, in reality, you're going to find this on your calculator and you're going to multiply that by this matrix here. And when you do, you find x, y, z equals 1, 3, negative 1, meaning our point 1, comma 3, comma negative 1 is where these 3 lines intersect. We can find the determinant of a 3 by 3 matrix by using the following. A, B, C, D, E, F, G, H, I is a 3 by 3 matrix. The absolute value symbols mean let's find the determinant. It's going to be upper left-hand corner A times lower right-hand corner. So A times, again you see the absolute value, that's the determinant of a 2 by 2, E, F, H, I, which would be the down products E, I minus H, F. Here's the key, minus whatever's in the middle here, B, minus that B, and the B is going to be multiplying by the determinant of the 2 by 2, D, F, Gi. We're going to split y. D splits y. Df, Gi. So that's Di minus Gf. Plus, now notice the signs go plus, minus, plus, whatever C is, times De, Gh. That's a 2 by 2. We're going to find the determinant of that, which is our down product, Dh, minus our up products,